So let's begin lecture 3. This is the course on corrosion protection methods. And this is lecture 3. And the topic what we will cover in lecture 3 is material composition and microstructure, and we will concentrate on metals and alloys. So in the last lecture what we talked about different conditions, the environmental conditions rather, the metals and alloys component experiences. Now that is dependent on whether that particular component is used in air or atmosphere, or it is under use in soil or aqueous medium. Now then we realize that material information is also important. So we have to talk about some of the important factors related to material which will govern corrosion, considering that the environmental condition is fixed. So if we try to list down those factors, the major two factors that come up is composition and microstructure. So now if we talk about composition, so when we talk about composition, it can be elemental form or alloy form. In majority of our applications we use alloy, not elemental form has a very limited application field. Now if we talk about elements, there are elements like aluminium, chromium, silicon, copper, nickel, iron, titanium, all those elements are there, and from there we make components, engineering components. I think we can mention zirconium, we can mention hafnium, all those elements are there. Out of those elements, some elements are there which have inherent high corrosion resistance, and that is decided by the position of those elements in the electrochemical series. Since it is a pure form, so we can consider electrochemical series, and when we talk about electrochemical series, we talk about standard electrochemical series. And according to the standard electrochemical series, like gold as well as iron, if we consider their position, so the gold will be sitting at a very high level in the electrochemical series, and the iron will be at a very low level in the electrochemical series. And when we see some elements which are sitting above, they have very high degree of inherent corrosion resistance rather, and whereas the elements which are below, those elements have a low degree of corrosion resistance. Now such examples are basically, let us say, gold, Au, platinum, palladium, even to some extent silver. So they are sitting at a very high level in the electrochemical series, and in that electrochemical series they are called noble metal. And whereas if we see some of the elements like iron, zinc, magnesium, they are sitting in the lowest position. Magnesium is towards the lower level in that series, and those are called active metal. So this is as per standard series. You can go to the one of the standard in the internet, you just look for standard electrochemical series, you will see that these elements are on top and iron, zinc, magnesium, those are at the bottom. Now, there are few elements which are sitting at the bottom, but interestingly they do have bit higher corrosion resistance because of the interaction with the environment. For example, some of the elements like aluminium, chromium, silicon, they actually are in the electrochemical series, they are at the bottom level, but still they have fairly good corrosion resistance. And the reason being the ability to passivate. And when we talk about passivate, we talk about the formation ability of impervious oxide layer. So, in case of Al2O3, SiO2, Cr2O3, these oxide layer forms on those metals when those metals are exposed to environment, and they can give a good amount of corrosion resistance. So, this kind of information will not be provided by the standard electrochemical series, and those are provided by a series called galvanic series, which is more practical rather than standard electrochemical series. Now, these are about the elements. Now, most of our applications use alloy forms like aluminum alloys, chromium is used in the alloying for alloy form with iron, silicon again it is used with along with iron, copper there are copper based alloys, there are nickel based superalloys, titanium based alloys, zirconium based alloys, those alloys are there. And when we talk about the when we say that iron based, that means the iron content is the maximum mostly. Now, those cases, some of the elements if we add into that alloy system, we get a fairly good corrosion resistance again. Like when we talk about iron, so iron can have two states, one is passivated condition, passivated state, one is active state. So, when it is active, then it would have a high level of dissolution rate. When it is passive, again the surface is covered by a passive layer, which is either oxides or hydroxides. Now, when we talk about galvanic series, which is more practical series, galvanic series, and galvanic series is basically environment specific. For a particular environment, we have to design the galvanic series. Design means we just have to connect these two metals or two alloy system in that particular electrolyte and see which way current is flowing. If the current flows from A to B, then we have to see current flows. So, what happens? Let us say we have this is A and this is B. So, now we have this is an electrolyte, this is an electrolyte, let us say some electrolyte, we connect them. So, if current flows from this way to this, that means electron flows this way to this. So, this will be anode and this will be cathode. Okay. So, this current flows through the conductor, and in the electrolyte we have current flow from B to A. So, then we can say that A alloy is sitting on top of B alloy, and this is the galvanic series in that particular electrolyte. Like that way we can form different galvanic series. Now, when we talk about this condition, we can say that this is in a particular system, like let us say highly oxygenated solution, or let us say concentrated nitric acid, and in one case it is a dilute nitric acid. We can have one in a concentrated nitric acid, we can have passivated condition where the corrosion rate initially would be very high, then it will reduces to a great extent. And whereas if we have plain iron, okay, almost nearly 90%, 99% pure iron, if we dip it in dilute nitric acid, it will not passivate, it will continuously dissolve. So, that means that time we can have this one would be sitting on top of, in that galvanic series, passivated iron will be on top of the active iron. Same metal, but behaving differently. Okay. So, now similarly, some of the elements which are very strong passive forming elements like chromium, like silicon. Let us have an example. So, we know that stainless steel, if we consider 304 grade, which is nothing but around 0.08% carbon, 18% chromium, 8% nickel. We popularly call it 18-8 stainless steel. And the microstructure is nothing but, it is not about the microstructure, the crystal structure is austenite or FCC. Okay. And the microstructure is all basically austenitic grains are there in that particular stainless steel. Now, because we have a very strong passive forming element, passive layer forming element, which is chromium, so there chromium oxide layer would form. It is not simple chromium oxide, it will be a mixture of chromium oxide as well as iron oxide. So, that layer would be so strong that it would not allow that particular material to get corroded, and the material would look shiny all the time. Fine. So, this is a typical behavior of stainless steel. That is what it does not have stain. A stain is nothing but the rust, and the rust has a typical color which is brownish or blackish brown color whenever the rust forms on iron. Okay. Because of that chromium addition, it gives you that very property of stainlessness. Okay. So, now when we have this is a typical compositional effect. So, that is what we are discussing, compositional effect. But interestingly, when we have this composition, but if there is a change in microstructure, we will talk about microstructure part later on, we will see that this material will be a very susceptible material to intergranular corrosion. We will talk about it, but let us concentrate on the material composition part. So, this is another composition effect. Let us say we have another steel, high silicon steel. So, high silicon steel typical composition could be like this. Let us see, silicon could be of the order of 14 to 16%, chromium of the order of 4 to 5%, manganese of the order of 1 to 2%, and carbon could be 1.2 to 1.4%, and rest of course iron. So, this is on typical high silicon steel. You know, this steel is not having much of ductility, but it has very high degree of corrosion resistance. And the typical use of this high silicon steel is auxiliary anode for impressed current cathodic protection. So, in short we call it ICCP. So, we will talk more about this ICCP later on when we talk about cathodic protection, as well as in connection to that we will come to know the anodic protection also. We will talk more about this, but at this moment we see that because of those passive forming elements, passive layer forming elements, we have a serious degree of corrosion resistance. Now, what is the use here? What we do, for example, this particular steel, let us say steel material component is to be protected, it is in the soil. So, what we do, we connect it to a DC power source, and this is connected to one high silicon steel. Okay. Now, when we have this, see this electron will flow this way. So, that means this would become cathode, and in any electrochemical cell, if something is cathode, that actually goes into a protection mode. and current will flow this way, and the current will come out from this. This will be anode, and then current will enter into this. As per cathodic protection principle, wherever current enters metal surface through the electrolyte, so that surface protected. So, this is the basic theory of cathodic protection. Fine. Now, in this particular instance, this high silicon steel is actually acting as an auxiliary anode which does not dissolve, it only is there to maintain the circuit. Okay. So, that is what this high silicon steel is used, and this external power source, which is definitely DC power source, that means all the time the cathode remains cathode. If it is AC, then the situation will be different. One time it will be cathode, one time it will be anode, there would be possibility of dissolution when it is anode. So, that is what it has to be connected to DC power source all the time. Now, here high silicon steel, because of its very property of passivating nature, it does not dissolve, but still it acts as a conducting path for the electricity to pass through the electrolyte and into the steel object which is to be protected. So, this is again the typical influence of the alloying elements or the composition. Like this, there could be several such examples. Now, when we talk about composition, then sometimes we have to decide the composition depending on the requirement, right. So, for example, if the locality or the region, geographical location where electricity is cheaply available, that time we can definitely go for ICCP and auxiliary high silicon anodes. But now one can also use graphite, because graphite is a very good very good auxiliary anode, but the graphite problem is it is very brittle. So, that is what, while operating, while handling it during installation, if it breaks, then the purpose is lost. So, that is what the material for this particular case, it should be strong enough, at the same time it should not have quite a lot dissolution, that means the self dissolution tendency would be as minimum as possible. So, that is what we designed this way. So, now you see the effect of compositions. Now, when we talk about composition, at the same composition one can develop several variations by changing the microstructure. Now, one way is you change the composition, another way is you fix the composition, you change the microstructure by applying a suitable processing routes, and then you can also have quite a good amount of corrosion resistance. Now, that is also, the processing route can also be incorporated as a trick or a kind of way to prevent corrosion in a particular material. How? By changing the microstructures. The typical example, again I am coming to that example. So, now once we know composition, so then we have to see microstructure. Okay. So, as we know that if we consider simple let us say 304 stainless steel, stainless steel. So, this is containing 0.08% carbon, as well as chromium is around 18% chromium. And this 18% chromium, if it is present homogeneously in the matrix, irrespective of it is present in the grain boundary, or it is present in the grain body. So, that means if we see a microstructure, so this is let us say a microstructure, and of course, this is a multigrain structure or polycrystalline structure, okay, and it is everywhere it is austenite, and these are the grain boundary. And this is grain body. Now, chromium should be present uniformly, and everywhere on an average it should be 18% of weight percent of chromium. So, when it is 18 weight percent of chromium everywhere, so then whenever it is exposed to the corrosive, it will form a kind of uniform chromium oxide layer. So, it will be passivated uniformly over the grain boundary as well as grain body. But if there is a change in the processing, let us say during welding of two blocks of 304 stainless steel or two plates of 304 stainless steel, if we use a slow cooling after you finish your welding, and this welding is you have to go to the molten state, and when you cool it slowly, and if it is cooled slowly between around 450 to 700 degrees Celsius, around that temperature, there could be possibility of chromium carbide precipitation along the grain boundary. Okay. So, now this structure changes if we slowly cool after you weld it. So, the same particular microstructure will change to this chromium carbide will form along the grain boundary. And now, when chromium carbide forms, near that grain boundary there will be a small patch. I am just putting it in the green color, that patch near to that grain boundary will have very low level of chromium. So, that means in this zone, except those chromium carbide precipitated points, those zone will have chromium content maybe less than 2%, which is not sufficient to form a continuous passive film. So, now this region will have 18%, that means all those positions, and everywhere in the grain body except those narrow pathway along the grain boundary, and also those particular region where chromium carbides are precipitating, those region also will be having very high level of chromium, more than around 21%. So, those wherever the chromium content is more than 18%, passive layer would form, but see in the patch zone we have chromium less than 2%. So, there chromium carbide will not form. Now, what would be the effect? Effect is you will see that this grain boundary region, which is we can say band, narrow band, that will be active sites, and rest of the region, rest will have passivity, and here we do not have passivity, no passivity. So, now you have two zones. Here you have a huge area cathode wherever passive layer has formed, and in this zone it is a narrow anode. And we know from our earlier understanding that if you have a large cathode and small anode, then it is a very bad condition, and that condition might lead to a severe dissolution of that narrow anode region. Okay. So, then this particular condition would lead to severe attack along the grain boundary band, and this leads to one dangerous corrosion event, we call it intergranular corrosion. Intergranular corrosion can lead to a serious failure if stress is associated with it. So, that means if we have this, now there is a serious dissolution along this, and let us say stress is acting like this. So, this will continuously open up the crack and then it will flow through that particular region and catastrophic failure can happen. So, we call it intergranular failure. Okay. Now, this is another part what I would like to mention, that the microstructure plays a big role even if the composition is same. Now, how to prevent it? Now, once we understand this, we should be able to have a kind of way out for this particular serious damage pattern. The best way to prevent is we process it, process in such a fashion, such a way that rapid cooling near the temperature zone around 450 to 700 degrees Celsius. Around that zone, if we cool it faster, then of course this chromium carbide will not form along the grain boundary. If we don't form chromium carbide, that means the chromium is staying in the solution and it is uniform all over the places near the grain boundary as well as the grain body, and that band, narrow band is not forming where chromium content goes below 2%, and then we do not have such problem of narrow anode as well as large cathode, and then the problem of intergranular corrosion can be avoided to a great extent. So, that means if we understand microstructure part, we can actually devise our protection route, and when we devise a protection route or design a protection route, you will see that we do not have to do anything externally over the material, rather you change the process parameters, you can change it. Like we do not have to go for coating, we do not have to go for any cathodic protection, we do not have to go for any inhibitor business. So, but we simply change the processing route, we can have a protection route. So, that means that is what I am trying to emphasize, that we have to understand environment, we have to understand materials also, and in the materials part, one part is composition, another part is microstructure, and microstructure is in the hand of processing route. So, that means we have to know this particular circle, composition, microstructure and processing. So, these are internally connected, and in fact, they are also connected, So, depending on the processing, composition and microstructure, these are all connected, and finally, it lead to some property which is nothing but, if we consider only on the basis of corrosion, it will lead to high degree of corrosion resistance. So, that means it is again coming back to that material tetrahedron, which is nothing but so this is composition, or we can say composition structure at one end. Let us say you fix the composition, so then definitely structure is to be considered, then processing, then we have property, and finally performance. So, these material tetrahedrons become very critical for devising corrosion protection method. So, let us stop here, we will extend our discussion on the surface character of metals and alloy components, and we will see that by changing the surface only, we can actually get rid of corrosion to a great extent. Till then, thank you.